Shell method. Basically, as I said earlier, probably brought up by somebody who didn't like doing disk method when it was dy. They would prefer to not have the rectangles perpendicular to the axis of revolution. They would prefer them to be parallel. And if you take a look at this, it would pretty much look like a shell, like I told you the other day, almost like a shell casing after a bullet has been fired. Very close, except it doesn't have the bottom, I guess you could say. And so what we have to do is, what if that's the only thing right there that I had to find the volume of? A lot of ways you could look at it, but I look at it this way. We're going to say that this width here is very, very tiny, and we don't really have to talk about that very much because it's going to be the same thing that we did with width before. It's going to be either the dx or the dy, and it's going to get taken care of for us. But what we definitely have to do is we have to find out, well, how far is it all the way around, and how do you figure out how far that is all the way around? Circumference. And the way you can find circumference is take 2 times pi times r, right? That's circumference. And then what we have to do, though, is we have to do that, and we have to figure out, well, how far is that? And we're going to refer to that as the height. And then how wide it is, like I said, that's going to be very small, but how wide it is going to be important. But we're going to say that's very, very tiny in a lot of cases. Okay? It's very similar. What is the difference between this and washer method? Yeah, no subtracting necessarily needed.
The radius.
Let's review. What was, say, disk method was? Actually, there was no height in there, was there? Why was disk method pi r squared? Because when we looked at it, we had to find the area of the circle that was involved. That's why it's pi r squared. Here we have to find the circumference of what's involved, which is why it's 2 pi r. The formula. You could use either one to solve all of these problems. You could use washer or shell. It really boils down to which one's going to make the problem easier. Because I told you a lot of people went to this one because they didn't want to do dy's. Okay. So what we're going to do is we are going to be using this formula right there. Okay. For example, now our rectangles will be parallel to the axis of revolution. So the one I have here is, what if you were going this way? Okay, is the one that I've shown for you. This is actually the harder one. Because if I'm going around this axis, which way should my rectangles be going? Horizontal or vertical? Just the rectangle itself that I'm going to revolve. Again, it should be parallel to the axis of revolution. Should the rectangle I draw be horizontal or vertical? Yeah, it should be going like this, right? And are there going to be a lot of those in there? Yeah, I only normally will show you one, but there are going to be a lot of them in there. Okay. Now do you kind of see that there is a shell involved? Now, here's the tricky part. You agree this is a dy, right? And do you agree that's this distance is dy? So of these two right here, which one am I doing right now? That one or that one? Horizontal axis of revolution. Now, the radius in this case of the shell, do you agree, is that distance? Okay, I'm just showing you where the stuff is now. We'll do an example to show you how to get the actual numbers. So that is the radius, and this distance is the height. Notice where the 2 pi has been placed. Does it have to be placed out front? No. It's just the safest place to put it, yeah. Okay. So again, this would be the radius. Okay. That there is the height. dy is your width. And your 2 pi's out front. Be 2 pi r h w. There they are. Okay. Just a visual for you. And integrating it allows that rectangle to move up and down. This is basically what happens. So let's actually try one and see what happens. Do I have the graph in there for you? Or no? No? All right, we'll get that graph in there then. It says calculate the volume for the solid of revolution formed by y equals x minus x to the third. The x-axis from 0 to 1 revolved around the y-axis. Let's take a second. It's just kind of a little hump. That's about all it is. Revolving around the y-axis. Do you agree if I was to have tried this, the other method, again, this is the other method, my rectangles would have had to have gone this way, right? If I tried the other method? Do you see how that could be a complication? Okay. But now that we're going to try shell, here's your axis of revolution right here. I want my rectangles to go this way because I want them to be parallel, which means are we doing dy or dx? Dx because it's hitting the x-axis. And so one of them would look something similar to that. Okay. Exactly. They would just kind of wrap right around each other. Yep. Okay. So what some of you are worried about probably is what about this one? You see how this one would be very tiny? And this one right here, if I put one right there, would there really be necessarily any hole there if I rolled that one around? No, there wouldn't necessarily be a hole there. Would there be a hole if I did this one? Right, yeah, there'd be a hole. But they would just keep continually going over just right next to each other, and they would eventually fill in. And would they fill in the same way that the disc and washer method did? Similar, but they would eventually fill in the whole thing. Okay. But the problem is the radius changes as we go, and so does the height. But looking at this, we are going parallel, so we know we are doing shell method. So what goes out front of shell method again? And why does 2 pi go out in front of shell method? It's always there because it's using circumference. Okay. What goes out in front of disk method again, just to see if you can keep it straight? Pi, because you're going to do pi r squared because you're finding the area of the circle times the height. That's the difference between the two. Now, seeing these are dx's, right? We're going from where to where?
0 to 1.
0 to 1. So, once again, the hardest parts. We're going to be finding the radius. And I believe actually finding radius is the hardest part. Finding the height, actually, you're probably getting very, very good at. Yeah, the height in this case, is it just the function? Because is that rectangle actually touching the bottom there? What if I go over here? Is it still just the function? And it wraps around this way? Yeah. So it is just the function. So in this case, the height is x minus x to the third. Again, I'm just writing it off to the side because I like to see if you can figure it out. The radius is the interesting part. Do you agree that the radius in this problem will be somewhere between 0 and 1?
Yes.
Now that just happens to be for this one because of where this is placed. For example, if I were to do, say, one that was right in the middle, do you agree that this distance would be a half? If I put one a little bit further over, perhaps that radius is 0.8, right? Perhaps this radius over here is very small. Maybe that's just 0.2. Nope, this is actually the best part. Do you agree that the radius is whatever x value I happen to place the rectangle at? Because if I place the rectangle in this problem at 0.2, is that the radius? What if I place the rectangle at 0.8? Is that actually the radius? Is it always going to work that way? No. But this is one of the first ones. We're just getting used to it, so we're going to keep it simple. So is it just whatever x value between 0 and 1 I happen to hit? It is. So the radius, very simple in this one, is just x. Because it's whatever x value I happen to use. And so what are we supposed to do? So it's 2 pi and then times radius, and then times height, and then times width is dx. Once we're done with this one, I'll show you how radius could be different, and then that might clear it up for you. Okay? Well, that problem right there, do you agree this is going to end up way easier than if we tried to do dy on this one? Try and change those rectangles going left to right like this. That'd be much harder in this one. And really, this one we could probably do quite quickly by hand. Everybody done with r and h? Know where they came from? All right. Let's go ahead and try it by hand then. We got a 2 pi sitting right here. Have I integrated yet when I write this down next, or no? No, because I got the squiggler. What is it? X to the, just distributing. Second minus x to the fourth dx. Because could we have done this one? Do we have a method to do it right from there? Does substitution help there? No. Integration by parts? No. So let's just go down here. We'll integrate that. So it's 2 pi, bracket, x to the third over 3 minus fifth over 5, 0 to 1. 0 is going to be a nice one again. Just got to check how close we are here.
Excuse the interruption. Chris Fritz to the high school office. Chris Fritz to the high school office.
So let's not forget the first thing you have to do is put in the top number, which is 1. So you put 1 in right there, and we get 1/3 minus 1/5. That's just putting in the first one, correct? And then you have to put in 0. Again, these zeros are always nice numbers if you can. So it is basically minus 0. But what have I forgotten at this point? Yeah, where's that 2 pi? Well, we better just do something like this. Oh, that's a really bad pi, but you get the idea. So we got 1/3 minus 1/5. We probably want a common denominator if we're going to do it by hand. 15 seems like a good idea. So 1/3 is what over 15? 5. It's just in disguise, right? And so it's 2/15 times 2 pi is 4 pi over 15. You could probably say units cubed because we don't know if this is inch paper or what this is, but that would be the volume. Again, way easier than doing dy on this problem. And maybe what I'll do here in a second is we'll talk about this. What if I moved the axis of revolution on you? How would the problem change? Okay? So does everybody have down what they want to have written down right now so I can erase this and try and show you how it might possibly change? Everybody's good? Okay. Yeah, that's not going to work. So we'll just get rid of it. All right. What if I didn't say y-axis? What if I said, say, something like x equals -1? We're just going to talk about it. You don't have to write this down. Let's just see what you come up with. Do you agree that would be somewhere over here then? Do you agree with that? That we're still revolving it around that. So let's just do, we know it's 2 pi out front still. Does the 0 to 1 really change? No, that's still the x's, 0 to 1. We still want to make our rectangles this way if we're using shell method, so it's still dx. So far, anything different? No. Radius and height. Does the height change? The height of that shell? No, the height's still the function in this case. What changes? Do you agree? Let's use a half. Let's put this at a half. Let's say that's exactly where I put it, was at 1/2. If I put that value at 1/2, is that actually the radius? Is 1/2 the radius? No, it's actually 1.5, correct? What if I put it at 0.75? Is 0.75 actually the radius? No, it's 1.75 is the radius. So it's basically just whatever the x value is, plus 1. Okay. Let's see how close we are. Pretty close. I think we'll make it. What if I were to put it over here, say at x equals 2? And we were revolving around that. Is the height the same? Height's the same. Is the 2 pi out front and 0 to 1 the same? Still dx's? Yeah. What's the radius? Let's say I was at a half. Let's say I put it there. Is that the actual radius? No, it's basically 2 minus that, correct? Would be the radius. It'd be 1.5. What if I put it at 0.75? Let's say I put it there. Is 3/4 the actual radius? No. It's 2 minus that, correct? So that radius is 2 minus whatever x value I happen to choose. And that's actually how I do it when I have a problem. I'm like, if I put the rectangle here, what's the radius? What if I put it here? What's the radius? That helps me figure out how to write it like this, symbolically. Okay.